basically where we left off, we were talking about, we had just been introduced to Lewis structures. We were putting them together, and we ran into some situations where there's more than one possible structure you could draw. And that's going to happen a lot, especially for things like, phosphate ions and nitrate ions and things where there's a lot of electrons and an imbalance of charge. So those electrons can move and set themselves up in a lot of different ways. And so this is an example. Whoops. Ozone. We sort of talked about ozone. And when we drew ozone, there was definitely more than one way of doing it. So let's have a look at how we did that the first time. So, all right. So ozone, we've got our 3 oxygens. How many total electrons are we dealing with? We have 3 oxygens. So how many total valence electrons
18.
do we have? 18, right. Oxygen is in group 6. So they've got 3 of them. 6 times 3, we've got 18. We've also got 2 of them, 2 bonds. So we've got 4 electrons used up in bonds. So that leaves us with 14. So we have 14 electrons. And as I mentioned previously, when we have electrons left over like this, first thing you want to do is generally decorate the outside of the molecule and make sure that they all have 8, an octet of total electrons. So we'll take those 14 and go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's 12. And now you see each of these oxygens have 8 on the outside. I'm just going to call them A and B. So they each have 8. They're fine. That's 12 electrons, and I have 2 left over. And any electrons you have left over go into the middle. So now you were asking about formal charges. This is a good time to look at formal charges and total electrons as well. So total electrons, A and B have enough electrons. They have 8. But poor oxygen in the middle, how many does it have total? Total electrons. Let's call that one C.
4.
It has 4 valence electrons. Yes, but how many total electrons does it have?
6.
6. Right. For total electrons, we consider all the bonding electrons plus the lone pair. When we're talking about valence electrons, we're talking about just the lone pairs and only half of the bonded electrons. Those are the ones I like to call the mine electrons, the ones that oxygen can claim just for itself. But as far as total electrons go, it would be all the electrons associated with that oxygen. And so either way, it has a deficiency. It has only 4 valence electrons, and that's not good. And it's got only 6 total electrons, also not good. So what we'll do is we'll move one of those, that pair of electrons from oxygen A into the middle. And so that takes that out. And so now oxygen A still has 8 electrons. We just moved a lone pair into bonding. C now has 2, 4, 6, 8 total electrons. So that's fine. And oxygen B on the other side still has 8. Now let's look at the formal charges. Remember, the formal charge, we just look at the number of valence electrons, not the total. And so each one of them should have 6 because they're oxygens. They should have 6, and then we subtract the number of valence electrons they actually have in this model. So oxygen A, how many valence electrons can it claim for itself? Yes, fair. 6, right? 6. It's got 2, this lone pair. It's got another 2, that lone pair, and it has this one and this one for a total of 6. Remember, we split all the bonds down the middle and share them equally. Now we'll learn today there's something else that we'll compute where we don't do that. But for now, we look for formal charge. We just look at the number of bonds each atom can claim for itself. And so A has 6, so its charge is 0. Now let's look at oxygen B here on the other side. How many valence electrons does it have? It's supposed to have 6, and we'll subtract the number it actually has. How many electrons in oxygen, how many valence electrons could oxygen B claim to have?
Seven.
That's right. This has 3 lone pairs, that's 6, and it has a bond. And so it keeps one of those as well. So it has 7. So the charge on this oxygen is minus 1. Now let's look at oxygen C in the middle. It's supposed to have 6 valence electrons. How many does it actually have?
5.
5, right. It's got its lone pair, so that's 2, and it has 3 bonds, so it takes an electron from each one. That's a total of 5. Uh-oh, so it has a positive charge. So there's a couple things wrong with this particular, well, one big thing that's a problem. We have an oxygen with a positive charge. That's very, very rare because oxygen is so electronegative, it generally pulls electrons from other atoms and makes itself neutral or negative, for instance. So in this situation, what we would see is because electrons like to go from places where it's negatively charged to places where it's positively charged. Electrons are negatively charged. That's the way they're normally going to move. That's how electron current moves, from negative to positive pole, right? So these 3 lone pairs on oxygen B, one of them is going to move. And let me just change colors so I have this. One of them is going to move that pair of electrons toward C and make another bond. So now oxygen B has no charge, and oxygen in the middle now has no charge because it has 6 valence electrons, but there's a problem. What is the problem with oxygen C in this situation? Oxygen C would look like this. What's the problem with that setup?
It breaks the octet rules.
And can it? I mean, that's okay. Some atoms can break the octet rule. Can oxygen?
It's in the second period, then yeah, it cannot break the octet rule.
Exactly right. Excellent. Yeah, it can't. Oxygen can't do that. And so, yes, the charge has been relieved of that oxygen. It's no longer positively charged, so es bueno. But now it has 10 electrons. That's no bueno. So this bonded pair then transfers back to oxygen A and gives it 6 electrons in lone pairs and a bond, and it becomes negative. So basically, those pair of electrons just move back and forth and back and forth and back and forth. And so we basically have 2 structures of ozone, and this is what they look like. We have the first one where the oxygen on the right side is negatively charged. And then we have the second version where the oxygen on the left side is negatively charged. Yes.
Why not like this? With
That's not what it's bonded like. It doesn't form that.
oh, okay.
That's because the steric hindrance of that is too much. That brings the oxygen molecules too close together. So we have these 2
Okay.
structures. And each one of them is equally likely. They're two different Lewis structures for the same molecule, but neither one is accurate. And the reason is because when we look at ozone, we can put ozone in a spectrophotometer. Now, a spectrophotometer basically just shines light onto ozone and looks to see what frequencies these bonds are stretching. This is a bond here that stretches like this. It moves back and forth. And it also stretches this way. So we can look at the frequency that these bonds both bend and stretch. And if it were the case that this was a double bond and this was a single bond, we would expect two different frequencies for stretching, one for a double bond and one for a single. We don't see that. We would also expect there to be two different bond lengths. Double bonds are generally shorter than single bonds. Single bonds are somewhat longer, because with double bonds, as we'll see when we're talking about bonding in the next chapter, that atoms have to be pushed slightly closer together to get double bonds to form. So double bonds are generally shorter, and triple bonds are even shorter than that. So we would expect two different bond lengths as well, and we don't see that. So what's going on? Well, what's going on is that we're actually seeing a mixture of both. We're seeing like a resonance structure. So as we were drawing the ozone just a minute ago, we saw that these electrons here are moving back and forth. They're moving to the left, and then they're moving to the right, back and forth and back and forth and back and forth. So basically, these are called resonance structures. The actual structure is going to be a little bit of both. Both of these can be accurate structures. Either one is equally plausible, but in reality, neither one is actually correct, because we see something akin to an average of both. So resonance structures have the same placement. The atoms are all in the same place, but they have different bonding and lone electron pairs. They all have the same total number of electrons. You get the total number of electrons by adding up all the valence electrons of all the atoms. That does not change. But the relative distribution of bonding electrons and lone pairs will change. They'll move back and forth, okay? So that's what a resonance structure means. What the actual structure looks like is basically, like I said, a hybrid of both of those. So you have ozone. It has more than one Lewis structure. And we'll see there's some molecules that have 3, sometimes 4 different Lewis structures that you could draw. And each of them, some may be more valuable than others. Some may be like less likely to occur than others. But you can have a lot of different structures. So just remember, though, resonance forms aren't real depictions, because ozone doesn't really change back and forth. We don't have a pair of electrons moving rapidly back and forth so fast that we see basically an average. The real structure looks like the average, but we'll see what it actually is an example of what's called delocalized electrons. So basically, we've been thinking that electrons are always going to be associated between either with one atom or shared with another one. Now, delocalized atoms are sort of spread over a few adjacent atoms. And we use dotted lines like this to represent them. And so you may think to yourself, that doesn't make any sense. I mean, how can that work? They can't be in all places at once. Well, this will also come to pass when we talk about polarity. Remember when we talked about electrons, when we sort of just started talking about the atom, the very first model of the atom was you had your positively charged nucleus, and then you had your electron, and it moved in circles around the atom. That's what Bohr thought, right? And so that model worked for hydrogen, but remember, it didn't work for anything else. And then when good old Schrodinger came along, he came up with an idea that atoms weren't actually, tiny chunks of matter. They were like waves, and that we couldn't tell exactly where they were, but they were, remember, it looked like they were sort of here. There was a distribution of electrons around the atom. You couldn't tell exactly where they were, but if you took the average distribution, they were going around the nucleus. Well, the same thing is true here. What's happening is that we have a distribution of electrons. Oops. We have a distribution of electrons here, distribution of electrons here, and here. We also have slightly less distribution here and here. So if you looked at basically like, where are the electrons in this molecule? There'd be a lot here, more here, and more here, and then there'd be a little bit less of a distribution in between. And so we would have these delocalized electrons. And what does that break down to? How can we explain that in terms of bonds? Well, we can really say it's sort of like half of a bond, really. We don't say it's half of a bond. We say it has a fractional bond order. So we don't say it's a bond and a half, but it kind of is. So here we have a double bond, so that would have a bond order of 2. And here we have a single bond. Well, that would have a bond order of 1. But we see with ozone, since we have this sort of equal distribution of electrons all the way around, we say that there's a total of 3 electron pairs. There's like 6 electrons there, and there's 2 places for them to be. So that's basically a bond and a half bond order. So we say it as a bond order of 1.5 or 1.5. Anyone have any questions about that? How that works? So remember, bond order, since we're not actually talking about a full bond, we say that it really, when you study it, when you look at it, the distance between these 2 oxygens and these 2 oxygens is in between what it would be for a single bond and a double bond. It's slightly less than a single bond, but it's not as much, but it's slightly longer than what a double bond would be. It's in between. And the distribution of electrons in between those oxygens is more than a single bond, but less than a double bond. So really, it acts like a bond and a half. I know it might be a little bit weird to think about, but just think of it as it's more than this, because remember, every bond is just a distribution of electrons. That's all it is. When we have 2 atoms, let's say we have just 2 hydrogens. Remember, all that bond is just a distribution of electrons in between them. And they're moving back and forth between the 2 hydrogens. It's just a distribution. So a greater distribution of shared electrons would be a double bond. An even greater distribution of electrons between 2 atoms would be a triple bond. Well, there are distributions in between those things, and we're going to see those fairly frequently. This is an example of the difference between a double and a single. We'll also see other examples. So let me clear that out. So let's do an example right here. We have nitrate ion, so NO3 minus. We want to write our structure of it, see where the formal charges are, and then see what sort of different resonance structures we can draw from it. Okay, so nitrate ion. So NO3. So who goes in the middle? NO3 minus. So who's going in the middle of this particular nitrate ion sandwich?
Nitrogen.
Nitrogen. Why is that?
It's the least. It's to the left more of the periodic table.
Yep. Yeah. So basically, there's a lot going against it for like not being in the middle. One, it's the only nitrogen. Generally, if there's just one of a particular element, it's usually going in the middle. So strike one. Two, it can form more bonds than oxygen can. Oxygen generally only forms 2 bonds, but nitrogen can form 3. So strike 2. And then 3, it's less electronegative than oxygen. Most things are. Only fluorine is more electronegative than oxygen. So if you're paired with oxygen, generally you're going in the middle. So, yep. So nitrogen's going in the middle. There's not much it can do about it. So here's our 3 oxygens, and we do 1, 2, 3 bonds. So how many total valence electrons do we have in this structure? How many does nitrogen have? What group is nitrogen in? I'm assuming everyone has their periodic table right in front of them.
5.
5, yeah. It has 5. And oxygen, as if we didn't know by now, has how many?
6.
6. Talked about oxygen a lot today. So 5 and 18, that's 23. Are we done? Is that the total number?
No, we have another electron to account for.
That's right. It is a charge. So we add that one for a total of 24. And that's something to look for when you're doing these. Almost always there'll be an even number of electrons, because electrons like to be, like they travel in groups, they travel in pairs, right? There's lone pairs, there's bonded pairs, pairs. So if you have an odd number of electrons, that should set off a little alarm in your brain saying that's something wrong there. Look for a charge. Either you're taking electrons away if it's positively charged, or you're adding them if there's a negative charge. So we have 24. So decorate the outside with electrons. Give everybody an octet. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 18. And then how many electrons are in bonds?
Six.
6. So 18 plus 6, oh, that's 24. So we're done. That's all the electrons there are. So let's look, and now we want to look at the formal charges. So now's the time to look at the formal. Once you've got all your electrons dealt with, you got none left over, now you want to look and see, does this make sense from both a total, from the octets, does everybody have an octet? Is everyone happy? And are there a lot of formal charges? So let's look. So we've got oxygen, let's say oxygen A, oxygen B, and oxygen C. So oxygen A, B, and C are all the same. They all have 6 electrons in lone pairs and a bond. So they should have 6 valence electrons. How many do they actually have? Valence electrons.
7.
7. So what are the charges in all those oxygens?
-1.
Yeah, they're all negative. So 1, 2, 3. So let's look at nitrogen. What is the total number of valence electrons nitrogen should have? What group is it in?
Should add 5.
Should have 5. How many does it actually have in this structure?
Only 3.
Only has 3. 1, 2, 3. Poor nitrogen only has 3. So what's the charge on nitrogen?
+2.
Plus 2. So there's some problems with this structure. One, there's a lot of charges. Now, does this make sense? Do all these charges add up to the correct charge? If I were to add up all these charges, do I get -1?
No,
Yes.
You do, right? I mean, there's 3 negatives and there's 2
Oh,
positives. So you add them all together, you get -1. So it kind of work. I mean, yeah, that is a structure you could draw, but is it a good structure? The answer is not really, because you have way too many charges. It's okay to have, some charges, and the charges are, if you have negative charges, they're on the right atom. Oxygen is more electronegative than nitrogen. So if someone's going to be negatively charged, makes sense it's going to be oxygen. But in this situation, you've got a +2 charge in the middle, and that's going to be pulling on electrons in a big way away from the oxygens and then into the middle. So generally, what's going to happen here is that this pair is going to go in the middle, form a double bond, and then give nitrogen a +1 charge and get rid of this negative charge. So now this oxygen now has a double bond and 2 lone pairs, which is typically, that's what oxygen looks like. It has 2 bonds and 2 lone pairs. So there's no charge there. And now nitrogen has a +1 charge, which is a little more doable than before. But the other thing we can actually do is move another. If we want to get rid of the charges completely, we can move another pair of electrons to the middle. And so, can we do that though? Can we have nitrogen with a total of 10 electrons? Can we have nitrogen that looks like this?
cool.
Does that work? I mean, that's five valence electrons. That's how many nitrogen has. Can we do that?
I think it would be too many total electrons.
That's right. Nitrogen can't violate the octet rule. It's only in the second period as well. So if oxygen can't do it, nitrogen can't do it either. So basically, we're stuck with nitrogen having a positive charge and 1 oxygen being neutral and 2 oxygens being negative. So 2 negatives, 1 positive, and that's what we're going to. So we can't make this particular structure. That's not going to happen. So we're sort of basically we're stuck with this. But where's my? So negative, negative, positive for a total charge of -1. Now, where the resonance structures come in is that double charge can be on oxygen A, it can be on oxygen B, or it can be on oxygen C. Each one of them is equally likely. And so we get resonance structures that look like this. So we've got double bond in one direction, you got the double bond pointing up, double bond pointing left, double bond pointing right. So we have 4 shared pairs. 2 here, 1 there, 1 there. 2, 1, 1. 2, 1, 1. Total of 2, total of 4 bonded pairs and 3 places to put them. So we have a bond order of 1 1/3. So what that means is that the distances between the nitrogen and the oxygens, they're all the same. And they're all slightly shorter than a single bond, but a lot longer than a double bond. And the average is closer to what a single bond would look like than what a double bond would look like. Okay? Does that make sense to everybody? How that works? If you wanted to know the bond order, look and see how many total bonds are forming and how many places are there. So we see that there's 3 places to form bonds between the central atom and the atoms around it. There's basically 3 areas of electron density. And how many bonded pairs are in those 3 areas of electron density? Well, in this instance, there's 4 of them. 1 double, that's 2. 2 singles, that's a total of 4. So there's 4 pairs of bonded electrons in these 3 regions where bonds go. And so the average is 4/3. And that's our bond order here. So any questions about bond order? I want to make sure that you understand this. This is going to come up fairly frequently.
Professor, can you explain what bond order is again?
Sure. So when we go back to looking at the difference between the old way of looking at bonding and the new way of looking at bonding. Well, the old way of looking at electrons was as, little spheres that went around the nucleus. And so when we looked at a bond, let's say we had a carbon-carbon bond. What the original thought was is that we had 2 electrons, 2 little things, one there and one there, and they were being shared by that electron. So we had these 2 electrons are basically moving back and forth. Between these 2 carbons, they were sharing these 2 little balls, and that was a bond. Well, then later on, we learned, well, that's not really correct. Electrons can't be considered just these little balls of matter. They act more like waves sometimes. And waves have a distribution. We can't say exactly where those electrons are. We have a density. So a single bond would have a density like this. We don't know exactly where that pair of electrons are, but they're somewhere in here. And where they are in space is between those 2 carbon atoms. That we can say for sure. There's a distribution, and that's where they are. Now, if there's a double bond, we have a greater distribution of electrons in between those 2 carbons. And if there's a triple, even more. So we have an even greater density of electrons in between those 2 carbons. But what if there's somewhere in between? What if we have a distribution of electrons that's more than a single bond would be, but less than a double bond would be? What do we call that? We call that the bond order. So in this instance, we have a double bond that could be there and 2 singles, and then we just count the total number of bonds. The total number of bonds is 4. Well, what does that mean? That means that there's 4 plus 4, 8 electrons distributed around the central atom. The central atom is nitrogen. That means there's 8 bonding electrons around the central nitrogen. That's all that means. 2 doubles, one double and 2 singles. That means just a total of 4 bonding pairs. That's 8 electrons distributed around the nitrogen. Well, what we learned is that they're equally distributed around the nitrogen. That distribution is even all the way around. So we don't really see 1 double bond and 2 single bonds. We see an even distribution. One thing I've sort of been trying to make clear in the class so far, Mother Nature loves symmetry. if you get down to like there's two structures you can create, one is symmetric and the other one isn't, there's more likely that symmetry will be held. Why? Because symmetry is a lower energy distribution of things. If something's symmetric, that means it's even all the way around. And you don't have, because anytime you have more electrons in one place than another place, that sets up a dynamic distribution. There's going to be some movement back and forth. If it's evenly distributed all the way around, that's much more chill. And that is true here. We have an even distribution of electrons all the way around the nitrogen. But instead of there being, if we have 6, we have 3 bonded pairs of electrons around the nitrogen. That's 3 single bonds. That makes sense. What if there's 4 in 3 places where you can have bonds? Well, that means we have a bond order of 1 1/3. So the way that these bonds behave is that they're not single bonds and they're not double bonds. They look slightly more like single bonds than double because the electron density between those oxygens and the nitrogen is slightly more than a single bond, but not nearly as much as a double. It's in between. Does that help at all?
Yes, thank you.
All right. Cool. Yeah, because this is I want to really push this particular model because when we talk about polarity, this is going to come up again. Because basically when we have a polar bond, we still have this same distribution, but if I have a more electronegative atom, like let's say I have oxygen here and carbon, that is going to pull that distribution of electrons a little closer to the oxygen. And so this distribution becomes a little more dense on the oxygen side and a little less dense on the carbon side. And so now we set up a polarity where there's more electron density here. Electron density here is higher and the electron density there is lower. And so we have a slightly negative charge, not a complete negative charge, slightly, delta, a little, petit, a little bit of a negative charge here and a little bit of a positive charge there. And that's what polarity is. You have an unequal distribution of electrons. That's all it is. And so I want to sort of make that picture clear to you because then it'll make polarity make a lot more sense. And it makes a lot more sense to me too when I think about, I don't have ball bearings of electrons. They're in this place, they're in this place. No, we have a distribution, we have a cloud. And the cloud sometimes moves to one side and the cloud sometimes moves to the other side. So this should be pretty much review for everybody since I've been harping on it for a while. Formal charge. This is one of the last things you do after you make one of these models. First, make sure you get all your total electrons right. Make sure you have the total number of valence electrons. Once you've got that done, make sure that everybody has an octet if they need one. Hydrogen doesn't need an octet. It can't handle an octet. Most of the other atoms have octets in their outer shell. So everyone has an octet, good. Then look and see what are the charges. And remember, formal charge, and this is the charge an atom would have if the electrons were shared equally. And this is going to be big when we talk about something called oxidation number in a couple minutes. Formal charge is we assume that all the atoms are playing nice and sharing equally. Well, in this case, with ozone, they kind of have to share equally because they're all oxygens. They're all pulling on electrons exactly the same. They all have exactly the same electronegativity. So they're going to be pulling on electrons the same. So we add up how many valence electrons it should have. Oxygen should have 6, remember, and we did count it, how many they actually have. And those are the unshared electrons, the lone pairs, plus half. We just cut these bonds in half and give half of them to one side, one oxygen, and half of them to the other side. So we just consider unshared electrons and half the shared electrons. That's the total number of valence electrons. When we're talking about total electrons for the octet, we're counting some of these electrons twice, right? Because this oxygen, we're counting both those bonds, and then with the oxygen in the middle, we're counting those bonds again to see that everyone gets an octet. So that's the total number of electrons. That's what we're dealing with when we're filling the octet. For charge, for valence electrons, we're only considering half the shared electrons, the me, mine electrons. So the ones that it keeps for itself in the lone pairs, and the ones that go into bonds, half. So each atom gets to say, half of these bonded electrons are mine, half are yours. And that's how we come up with the formal charge. So when we look at the resonance forms for a structure, all the formal charges, when you add them all up, have to be the charge on the species, right? I mean, when we looked at the nitrate ion, we saw that, right? At the end, there was more than one way we could put it. So for nitrogen, for one of them, we had nitrogen with a +2 and all the oxygens with a -3. That added up to +1. Or we had a nitrogen with a +1 and 2 oxygens with -1 and another one with no charge. That added up to -1. So no matter what your resonance form is, if there's charges on it, they got to add up to the total. So if it's an ion, it's got to add up to the charge of the ion. And if it's a molecule, what should the charges add up to? If I'm drawing a molecule, ozone, classic example, there's ozone, there's another form of ozone. What must the charges add up to on ozone? It's a molecule, not an ion. What do the charges have to add up to? That's right, Ferris. You want to tell us?
0.
Yeah, it's got to add up to 0. It's a molecule. By definition, the charge on a molecule is bupkis, because if it wasn't, it would be an ion. It would be a polyatomic ion. So no matter where the charges are, and in this case, oxygen B, the one in the middle, is always positively charged. And it just varies as whether the one on this end or the one on that end is going to be negatively charged. But we have one positive and one negative. They have to add up to 0 because it's not an ion. So, questions that people have been asking me. How do I know which resonance form is the best? Which one is most reasonable? Here's some of the rules to go over for that. Smaller formal charges are preferable to big ones. Like for instance, with the nitrate molecule. With one, we had +2 nitrogen in the middle and 3 negative oxygens. Well, that's a lot of formal charges. And so it's more reasonable to reduce the charges when possible. And with that structure, it was easy to move a lone pair from one of the negatively charged oxygens into the middle and reduce the total charges. So smaller formal charges are better than bigger ones. Generally, you don't have like charges on adjacent atoms. Generally, you don't have a negative charge next to a negative charge. That usually doesn't occur. It may sometimes, maybe there might be no other way to draw it, but generally you don't have the same charge on adjacent atoms, like a positive and a positive or a negative and a negative. Because in that situation, basically what you're setting up is a molecule where 2 of the atoms are repelling each other. And that's exactly the opposite of what a molecule is supposed to be doing. right? I mean, a molecule is supposed to be bringing atoms close enough together that they can share their electrons, but not so close that the nuclei start to repel each other. So there's a happy medium, close enough where where electrons can be shared, but not so close that they repel each other. As you put the like charges on them, they're repelling each other, and that's unstable. That's not a stable situation for a molecule to be. They're going to be pushing apart and at the same time causing a big strain on those shared electrons. You're going to be moving further and further apart from each other. And so it makes it more and more difficult to share electrons. So avoid doing that if at all possible. And one of the other things we saw with the nitrate ion is if you have negative charges, they should be on the more electronegative atom. So oxygen is more electronegative than nitrogen. If there's going to be negative charges around, they should go on the oxygen. Now, there are going to be exceptions to this rule. One of the exceptions is carbon monoxide. Carbon monoxide basically has an equal distribution of electrons with a triple and then in the middle, and then a lone pair on each side. But in this situation, that gives oxygen a plus charge and carbon a minus charge. That shouldn't happen. But this comes back to the old Mother Nature loves symmetry, because there's a symmetrical distribution of electrons in this particular situation. And this oxygen is more electronegative and realistically pulls the distribution of those bonded electrons toward itself. So when we look at carbon monoxide, we say, well, I mean, there should be an unequal distribution of electrons because carbon is negatively charged and oxygen is positively charged. But oxygen is so electronegative, it pulls those shared electrons, that cloud, the distribution of electrons toward itself. That basically now we have a relatively equal distribution of electrons. Carbon is more than it should, oxygen is less than it should formally, but oxygen pulls the cloud closer to itself. And we have what's called a polar nonpolar molecule. We'll talk more about polarity in a little while. But carbon monoxide is both polar and nonpolar. I was asked about this earlier in one of the recitations, and I posted an article about carbon monoxide since it's so interesting. But that is one of the few examples where the more electronegative atom does not have the negative charge. And again, the only time nature breaks these rules is in the interest of symmetry. Symmetry trumps all, pretty much. So any questions about these three rules? Smaller charges, when at all possible. Don't have like charges on adjacent atoms, if at all possible. And then if you got negative charges, they should go to the more electronegative atom. So let's do an example. Come on. There we go. So here's cyanate ion. And so we have, oops. All right, we have NCO. So how many total electrons should we have in this particular ion? How many on nitrogen?
5,
5. So 5 here. Then how many on carbon?
4,
And oxygen?
6.
6. So 15. odd number. What's going on?
You forgot the charge.
I did forget the charge. 16. So I want 16 electrons. I got 4 of them in bonds, so I got to put 12. So as usual, I fill up the octets. So to fill up the octets and the oxygen, I need 1, 2, 3, 4, 5, 6. To fill up the nitrogen, it's got 1, 2, 3, 4. That's not enough. 5, 6. All right. So now I've got all my electrons, but I have some obvious difficulties with octets. So nitrogen has an octet, oxygen has an octet, but poor carbon does not. So what am I going to do with the carbon to get it the octet it needs?
You could give it a double bond between oxygen and nitrogen.
I can't put a bond between oxygen and nitrogen because they're not bonded to each
No,
other.
I mean a double bond between nitrogen and carbon, and then a
Yeah,
double.
okay. There we go. So we'll move that pair of electrons into the middle. And so let's get rid of these. Okay, so now nitrogen still has its 8, but carbon still only has 4. So what
And
are we
then
going to do?
A double bond between carbon and oxygen.
There we go. Let's do that. So we'll move this lone pair in between. And so, let me get rid of these two. Okay, so that's one potential structure. So everybody has 8 electrons total. Everybody's happy. Now let's look at the valence electrons. So how many valence electrons should nitrogen have?
5.
5. How many does it actually have in this situation?
6.
It actually has 6. So the charge on nitrogen is -1. And what about carbon? How many valence electrons should carbon have? It should have 4. How many does it actually have in this situation? And if you ever wondered, do that trick like my old ex-student and just put electrons in every one of them. And it does make it a lot easier. 1, 2, 3, 4. It has 4. So no charge on the carbon. What about the oxygen? It should have 6. How many does it actually get to call mine, mine, mine?
6.
It's got 6 too, right? It's got 2, 4, and then these 2. 1 bond, 2 bonds. 6. So that's a structure. It has relatively low charges, only got 1, and everybody has an octet. What's the problem with this structure? Anyone see a problem with it? Based on the rules we just learned? If there is a negative charge to be put on a atom, what should it be?
Should it go in the middle on the carbon?
No, it didn't say anything about it had to be in the middle.
Okay.
Be on the oxygen since it's more electronegative.
Right, there you go. Yeah, it should be on the most electronegative element in the molecule. Well, nitrogen's pretty electronegative. It's more electronegative than carbon is. That's true. But it's not as electronegative as oxygen. So another structure that can form is we form a triple bond between the nitrogen and the carbon. And then this gets kicked out to put another lone pair on that oxygen. So what we have then is that this pair goes away. this bond goes away, and we're left with this structure. So what are my charges this time? So nitrogen should have 5. Valence electrons. How many does it have here?
5.
It has 5. It has the lone pair, that's 2, and 3 bonds, 1 from each bond, that's 5. So there's no charge on the nitrogen. What about the carbon? Should have 4. How many does it actually have? Valence electrons.
Four.
Yeah, it's got 4, so there's no charge on the carbon. What about the oxygen? It should have 6. How many does it have?
7.
Yeah, it's got 3 lone pairs and a bond for a total of 7. So it's negatively charged. And that makes more sense. Oxygen is more electronegative than nitrogen. So if anyone's getting that extra electron, it's going to be me, it's going to be oxygen. But there's also yet another version you could make, where this time the oxygen has the triple bond. So we go 1, 2 for a triple, and then 1, 2 on the nitrogen. So in this instance, we have this. Now, what are the charges in this particular structure? How many electrons does nitrogen, let me erase one more. So how many, nitrogen should have 5 valence electrons. How many does it have in this structure?
Seven.
It has 7. So there's a charge of -2 on nitrogen. Carbon still has 4, so there's no charge on carbon. And what about oxygen? Oxygen is supposed to have 6 valence electrons, and how many does it have in this orientation?
5.
5. So the charge on oxygen now is positive. Now, this is really a bad idea. So not only does nitrogen have a negative charge where oxygen should, now nitrogen's twice as charged and oxygen's now positively charged. So this is really unlikely. So this particular structure would be the least likely of all the ones we have. So when we put all those 3 together, we look at them and we say, well, which one of these is preferred? Which one of these is the most stable, has the least number of charges, and the charges are in the right place? Well, resonance form 1 is not very important. It has negative charge in the wrong place, and it has too many charges. So if there's going to be some sort of contribution to what this structure actually looks like, not much of it is going to be that. Then we look at the other 2. So in this one, fewer formal charges, that's bueno, but it's the negative charge is on the nitrogen rather than the oxygen. And because oxygen's more electronegative, it's more likely that it's going to pull, and remember, as I've been sort of like blathering about all morning, all these bonds it's just a distribution of electrons. It's just a cloud of electrons, right? So oxygen pulls on clouds of electrons more than nitrogen does. So it's more likely that oxygen's going to pull that cloud of electrons closer to itself. And so this is the most likely resonance form. So when we look at them, we say that the overall structure is a weighted average. When they're all equally likely, like with ozone, you had one distribution and the other distribution, they were both exactly the same pretty much. So they're equally likely. So 50% look like that, 50% look like that, and you got an average. Well, in this particular instance, this is most likely. So the resonance structure is going to look most like 3, a little like 2, and nothing like 1. So the weighted average is going to mostly look like the third, not a tiny bit like the second, maybe a little bit of a more of distribution of electrons closer to the nitrogen, but mostly closer to the oxygen. So is the most important form, the third one. Okay. Any questions about that? Like why one is more likely than the other? Remember, when we're dealing with these clouds of electrons, the clouds of electrons are going to move closer to the more electronegative atoms. That's what electronegativity means. It means that if there's going to be a cloud of electrons between you and me, I'm more electronegative than you. They're going to be closer to me than they are to you. There's still going to be a cloud of electrons in between those two atoms, but the cloud is going to be distributed a little more closely to the more electronegative one than the less electronegative one. And when you have an unequal distribution of electrons, you have polarity. So this is talking about formal charge. Now I'm going to introduce a new concept called oxidation number. I think we will get into oxidation reduction reactions, hopefully before the end of the term. In other words, redox reactions are what they're called, for reduction and oxidation. Now, we talked about oxidation being an atom losing electrons. When it gets oxidized, it loses electrons, generally to oxygen, why it's called oxidation. Reduction is when it gains electrons. So for a formal charge, we're talking about, as I mentioned before, equally sharing the electrons between them. So if I have a carbon and an oxygen, when I'm trying to figure out what the formal charge is, remember I just split this bond down the middle. I give one of the electrons to carbon and I give the other electron to oxygen to figure out what the actual charge is. But when I'm talking about figuring out the oxidation number of an atom, all the bonding electrons go to whoever is more electronegative. And so in a resonance form, it doesn't matter where the formal charges are. The oxidation numbers are all going to be exactly the same because you can't change who you're bonded to. So the oxidation number of carbon, look at carbon is in the middle of this sandwich between nitrogen and oxygen. Nitrogen is more electronegative than carbon. And so all of carbon's electrons are going to go toward nitrogen and they're going to go towards oxygen. Carbon is basically not going to have much of an electron cloud around it compared to nitrogen on one side and oxygen on the other, because they're both more electronegative than carbon. And so when I add up the number of electrons that carbon gets to keep for itself, when I'm talking about its oxidation number, it gets to keep none, 0, doesn't get to keep any, because it has more electronegative atom on one side and a more electronegative atom on the other side. So those electrons from carbon, 2 of them go to nitrogen, 2 of them go to oxygen. And so carbon, poor carbon in the middle, has a +4 oxidation number, meaning in this situation, carbon can be considered to be oxidized because carbon by itself, like in graphite or something like that, is equally sharing its electrons with everybody. And so the electron cloud around each carbon is the same. But when it's bound to oxygen, when it forms CO2, or in this instance, when it forms cyanate ion, that electron cloud then gets pulled away from carbon towards the 2 more electronegative elements, and it becomes oxidized. And so we say that its oxidation number goes from 0, and the oxidation number of every element in its most stable form is 0. So carbon, when it's in graphite or diamond, is 0, doesn't have any oxidation number. When it's now bound to more electronegative elements, it loses those electrons to the other two and it becomes positive. Now, this is different from a charge. It's not positively charged. It has been oxidized. There's a difference. It means that it's not playing nice with the other two atoms that it's bound to. It's having its electron cloud pulled away from it, but not entirely. You need to have the electron cloud pulled completely from you in order to get a charge. To get a positive charge, you need to have an electron completely removed. Or to get a negative charge, you have to have an electron completely added. You're not sharing it unequally, you're keeping it. That's a charge. But for oxidation and reduction, it means that your cloud is either closer to you or further away. Okay? You see the difference between oxidation number and formal charge. Is that clear to everybody?
How do you determine oxidation numbers again?
Okay. So, great question. So, actually, that's a great segue. I will just go right to it. Electronegativities are used to assign oxidation numbers, okay? So, for instance, I'll go back to that example of okay. So the more electronegative atom is assigned all the shared electrons, not just some, all of them. And the less electronegative atom gets none. So basically, that means they're not playing nice. So when we're dealing with formal charge, we're assuming that every atom's playing nice and they're sharing their electrons equally. Well, in the real world, that's not how it works. More electronegative atoms will share an electron with you, but it won't share it completely. It'll share some electron distribution, but it's really going to keep most of it for itself. That shared pair of electrons is going to spend a lot more time closer to oxygen than it is to carbon. And so each atom in the bond gets all of its unshared electrons. So if it's a lone pair, it gets to keep those. Those are mine, mine, mine. So let's calculate them here. So nitrogen should have 5 valence electrons. So how many lone pairs does it have?
1.
1. So it's got those 2 valence electrons to itself. And then we also subtract all the unshared, all the shared electrons that it has next to an atom with a lower oxidation number, lower electronegativity. Oxygen's is around 3.5, I think. Nitrogen is around 3, and carbon's around 2. You should have a table of electronegativities in front of you. I did have one, but I couldn't find it this morning. But these are the relative electronegativities. So carbon has a higher electronegativity. Nitrogen has a higher electronegativity than carbon. So it keeps all of the shared electrons with carbon. And there's 6 of them, right? There's 6, 2, 4, 6. There's 3 bonds. There's a triple bond there for a total of 6 electrons. And it gets to keep all of them. So it's got total of 5 valence electrons, but it really has a total of 8 valence electrons. So its oxidation number is -3. Because it's got 1, 2, 3, 4, 5, 6. It gets to keep all the electrons that it has either to itself or shared with carbon. It gets to keep all of them. So that's 8, total of 8. So its oxidation number is -3. Now, let's look at oxygen. But let's change color here. So oxygen should have a total of 6. Oxygen should have 6 valence electrons. Let's see how many it has. It has 2, 4, 6, and this pair of electrons that it's sharing with carbon. Excuse me. Now that pair that it's sharing with carbon, it gets to keep for itself because it's more electronegative, bringing its total to 8. So it should have 6, actually has 8. Its oxidation number is -2. So -2. And the carbon, how many electrons does carbon get to keep for itself in this situation?
Wait, I'm sorry. Can you explain how you got the 8 again for the oxygen?
Oh, yeah, sure. Oxygen is 3. In that situation, oxygen, just look at that bond. 1, 2, 3, 4, 5, 6. So in this situation with this bond, the oxygen has 2, 4, 6 electrons in lone pairs. That belongs to carbon. Belongs to oxygen. So those 6 electrons, any electrons in lone pairs, that atom gets to keep. So it already has 6. So that oxygen already has 6. Then we look at the pair of electrons it's sharing with carbon. It's more electronegative than carbon. So any shared electrons with carbon, it keeps those too. So 2, 4, 6, 8. It gets to claim all of them because it's more electronegative. It has 6 to itself, plus another 2 that it's sharing, but since it's not sharing nicely, it's more electronegative. It keeps those 2. So it has a total of 8 electrons. So its oxidation number is -2. Now remember, this is different from formal charge. We're just saying that's how many electrons it gets to claim because it's more electronegative. So in that situation, nitrogen, we have nitrogen, carbon, oxygen. And so nitrogen is -3, carbon or oxygen is -2. How many electrons does carbon get to keep for itself? So if we want to figure out what the oxidation number is on carbon, we have to figure out how many electrons does it actually get to keep. Does it get to keep any? Remember, it has to be more electronegative than an element it's sharing electrons with to get to keep any of them. Nitrogen is around -3 or 3 electronegativity. Carbon is 2 and oxygen is 3.5. So carbon is the least electronegative element there. Does it get to keep any electrons? And there's quiet. So it's sharing 8 electrons, right? It's got a triple bond on one side and a single bond on the other. So there's a total of 8 electrons being shared with carbon. But because it's not as electronegative as either atom on either side, does it get to keep any when we're considering its oxidation number? For formal charge, it would get to keep half. It would get to keep 1 of those electrons from each of the bonds, and so it would have no formal charge. But for oxidation number, how many electrons does it get to keep? See rule number 1. The more electronegative atom is assigned all of the shared electrons. Is oxygen more electronegative than anyone here? That's right, Rye. No, it doesn't get to keep any. Very sad. So carbon is the least electronegative element there. And so it doesn't get to keep any shared electrons. It doesn't have any lone pairs, so that's 0. And all of its shared electrons are with more electronegative elements, so it doesn't get to keep anything. So carbon should have 4 valence electrons, and for an oxidation number, it has none. And so its oxidation number is +4. And your oxidation numbers should also add up to the charge. And so this particular ion is -1. We have -2 and -3 for -5, and +4 gives a total of -1. So that's how you know you figured out the oxidation numbers properly. We'll return to this when we're dealing with oxidation and reduction reactions. But it's also a good introduction to where polarity comes from. When you have big differences in oxidation numbers, you have polarities. So is that clear on how to do that? There's another example on the next slide. It's a little easier. So here we're just dealing with hydrogen chloride, or HCl. So we just have that. So let's look at 1, 2, 3, 4, 5, 6. So chlorine has the 6 valence electrons, 7 valence electrons. Hydrogen has 1. So chlorine is more electronegative than hydrogen. So chlorine has those 7 valence electrons, 2, 4, 6, 7. But it also gets to keep that 1. It gets to keep that 1 as well because it's more electronegative than hydrogen. So it pulls that charge, that distribution of electrons, this sort of cloud of electrons toward itself. And so it gets to, basically, it gets to keep it. So it has 7. We're giving it 8. So its oxidation number is -1. Hydrogen is less electronegative, so it has that 1 valence electron, and it doesn't get to keep it. So it becomes +1. So all the electrons are given to chlorine. So hydrogen's +1, chlorine's -1. And what you will see pretty much over and over and over again is that hydrogen is almost always +1. Oxygen is almost always -2. And the halides, like fluorine, chlorine, are generally always -1. Because oxygen needs 2 electrons to get to 8, and it's going to get them most of the time. So its oxidation number is going to be -2. Hydrogen is pretty much less electronegative than all the nonmetals, so it's usually going to be +1. And all of the halogens are really electronegative. They need just 1 more electron, so they're pretty much always -1. Now, things in the middle, like carbon and nitrogen, can vary radically. For instance, if we look at methane, carbon is more electronegative than hydrogen, slightly, but a little more electronegative than hydrogen. So carbon gets to keep all of the shared electrons, all of them. And so there's 8 shared electrons. There's 4 single bonds. That's 8 shared electrons. It gets to keep all of them. And so it should have 4 valence electrons. It actually has 8. So in this situation, carbon has an oxidation number of -4. Now, when we burn methane, we produce carbon dioxide. So when we produce carbon dioxide, we make this. Now, carbon, again, is sharing 8 electrons, just like it was in methane. But the difference is it's sharing them with oxygen now. Oxygen is more electronegative. So those electrons that it's sharing with the first oxygen go to this oxygen. Those two pairs of electrons it's sharing with the other oxygen go to that oxygen. And so carbon has no valence electrons that it gets to keep for itself. So this oxygen is -2 oxidation, that one's -2, and oxygen now is +4. So we say that oxygen has been oxidized. It has been, when it's bound to hydrogen, it's reduced, and when it's bound to oxygen, it's oxidized. So that's one of the things pushing that reaction forward. It's an oxidation reduction reaction going towards oxidation. So carbon varies its oxidation number wildly. So does nitrogen, but oxygen generally doesn't. The more electronegative you are, the more likely you are to have a negative oxidation number. The less electronegative you are, the more likely you are to have a positive oxidation number. So hydrogen's almost always +1, and oxygen's almost always -2. And if you're in between those two extremes, your oxidation number can vary tremendously. Okay? That's going to be it for today. Any questions about, we sort of went through oxidation numbers fairly quickly. Any questions about this or anything else we've touched on?
What does it mean when something is oxidized again?
Oh, when something is oxidized, it means it's basically its shared electrons with oxygen are being pulled more towards oxygen. So in the example I just showed you, when carbon is bound to hydrogen, it's more electronegative. And so it's pulling those electrons closer to itself. So it has a little higher electron density around itself than usual. So we say it's reduced because it has more electrons around it than it normally does. So it's reduced, it has more electrons. But when it's bound to oxygen, that electron cloud gets pulled away from carbon and towards oxygen. And so we say it's oxidized because that electron cloud that was so close to carbon in the presence of hydrogen is now pulled away from it in the presence of oxygen. So it's gone from being reduced with lots of electrons around it to being oxidized with less electron density around it. So its actual charge hasn't changed, but the electron cloud around oxygen has been reduced. It's been pulled away. So we say it's been oxidized. Okay?
Professor, I was going to ask if you could assume that the charge of a monatomic ion is the same as oxidation, but I think you were saying like it varies a lot, especially with like.
Wait a minute. So a monatomic ion, yes. So like if fluoride ion would have an oxidation number of -1.
Yeah.
Yeah, because it only has eight electrons and it's supposed to have 7 as an element, so its oxidation number is -1. On the other hand, if you have O2, the oxidation number on each of those is 0. And the same is with F2. Because basically it's pulling on electrons with itself, with something that's exactly the same. So that distribution of electrons does not change, it's equal. There's an equal distribution of this around this oxygen and this oxygen. They're exactly the same. And so the oxidation number is 0. Same with fluorine. Pretty much the only time the oxidation number of fluorine isn't -1 is when it's bound to itself. So we say that the oxidation number of any element in its most stable form is 0. And then when it reacts with something, it either becomes reduced or it becomes oxidized.
Thanks.
Yeah, no problem. Okay, so my two groups this afternoon at 1:10. We'll be doing the next recitation. It's posted in Canvas, so if you haven't seen it, download it. I would also recommend, I also posted these tables, which are the summary of electron density and corresponding shapes. So we're going to be looking at that a little bit today as well. So that isn't something that you're going to have to memorize. That's something we're just going to learn just by looking at the tables. You'll be able to refer to it. Okay, I don't want anyone memorizing this stuff. I can't memorize it. Use a table. So we'll pick up from this on Thursday, and we'll be doing the lab on polarity on Thursday as well. So if you're not sure what you're doing with AJ, yeah, just check in with him real quick. I'm pretty sure you're doing a lab. Okay. So that is everything. I will see some of you this afternoon and everyone else. I have office hours tomorrow at 11, or if you want to talk about something else, just drop me a line, okay? All right.
Thank you.
All right, thank you guys too. Stay well, everybody.